Record on this computer. Okay, we're recording. Anything you say can be taken in evidence against you. All right, you're all about to get an email from Dr. Robertson. In the lab packet, everything with the electric motor is due on Friday. The motor and stuff we'll be working on next week. Not a lot of people showed up for the lab sessions, so you'll have to rely upon email or text if you want to get any more help with the lab packet.
I was really confused about that and what I should have done. Like where can I find what to do for the lab?
There was a packet sent out by Dr. Robertson on the 24th.
Yeah.
I had a there was a follow-up message from me talking about the stay-at-home order, and so please pick up your packets right away. But the email before that in the chain is from Dr. Robertson with the lab packet.
So you said it was sent out yesterday?
No. 24th, did I say? It's 22nd. Phys 1600 labs.
Oh, the attachment was hidden for me. I just now saw the attachment.
Okay, anyway, well, that's where it is. So everything up to the electric motor is due Friday. If you have thoughts or comments on that, you can talk to Dr. Robertson or me. Robertson's organizing this, but I'm available to help with the lab stuff. So let's press on here. So let me hold on. I have to share my camera. Where's my mouse? Share screen, visualizer. Okay. All right. So let's get started. So last time, here's my daily review of what's going on. So the story up till now is we have magnets push and pull on each other, but digging into the details, what we find are a couple of basic facts. And one is that charges are pushed by fields. And specifically, if I have a charge and it's moving and it's in a magnetic field, then it'll feel a force, right? And so in this case, which way will the force be? Okay, people have their cameras turned off. Right, it'll be a force this way. V cross B into the page means that the force is upwards, right? And we can write that as the force on the particle is Q V cross B. And if we want to, we could add in the electric field, or sometimes we might even write it like this, V cross B plus E. And in fact, this equation has got a name. This is called the Lorentz force. And it describes how electricity and magnetism both act upon a particle. And we talked about this last time, that, for instance, this is the thing that happens in a velocity selector. There's a force due to the electric field and a force due to the magnetic field. And they add up to create a net force of the particle. Okay, so now if I have many charges moving, that means I'm going to have a section of, say, wire that's carrying current. Then that wire also feels a force. So if I have the wire in a magnetic field, then this guy feels a force. He'll again feel a force in the same direction, because there's positive charges moving to the right here, or negative charges moving to the left. Either gives you the same answer. And so this also feels a force, and this force is going to be I L cross B, which is the same sort of thing. In fact, when I'm doing these right-hand rules and I'm looking at a section of wire, how I tend to think of it is I tend to think it has a velocity. The charges have a velocity to the right. And so I actually think this equation when I'm actually doing this equation. Okay, so that is charges are pushed by fields. And then the other thing we talked about last time is that moving charges make magnetic fields, right? So if, for instance, I have a charge and it's moving this way, it creates a magnetic field that looks like that around it, and there's a smaller one behind it in front of it. And if we want to know what the field is at some position, so if I draw an arrow from the charge to some position here, P, and I call that arrow R, then that tells me, then I have the Biot-Savart law tells me how big that B field is. It says that B is equal to mu naught over 2 pi Q V cross R hat over R squared is the rule. Now this is a very complicated...
Didn't we decide it's 4 pi?
Oh, 4 pi, excuse me, you're right. I'm always writing that incorrectly. Thank you. Keeping me on my toes. So if, and so what we moved this to, so what we did at the end of the day last day is we said, well, this also then means that if I have a wire carrying charge and I have a wire of little length DL pointing this way, so I'll actually say that the wire is pointing to the right, the DL is a vector. Then, where's everything so cattywampus here? Let me see. Oh, I see. Camera is cattywampus. Okay. So if I have a little bit of wire here, that it creates, again, a magnetic field just the same way. But instead of describing it in terms of charge, I can describe it in terms of the current. So again, I'll take a little vector, I'll take a vector R that points at the place where I want to know what the B field is equal to. And so for here, I can find, let's call it a small B field. That small B field is equal to mu naught over 4 pi I times dl cross r hat over r squared. And so both of these are forms of the Biot-Savart law. So this is where we wound up at the end of class last time, as we said, okay, so if you have a little piece of current, a little piece of current carrying wire, it's this. Now this law by itself is actually quite useless because it's impossible to have a small piece of current carrying wire. Like as we learned in electricity, you can't just move charge this far. It has to form a loop if you're going to have current moving continuously. I have to somehow like get this current back to where it started. So this little piece here is not very useful, but we can make some useful approximations. So the first approximation we're going to do is we're going to try and figure out what it's like near a long wire. So I'm going to have a very long wire here carrying a current, and I'm going to want to know what is the B field in this position. So what I'm going to have to do is I'm going to have to add up the effect of the current going through this little piece and this little piece, and so I can call this a little DL here, right? It's got an arrow that way. So every little piece of the wire is going to contribute to making the B field here, and we have to add up all those contributions. So the first thing we have to know is which way is it? Okay, E's and F's. Fight to the death. Or somebody give in.
I picked F, which is into the page. Wait, which is into the page, because it would be going around. If you point your hand there and then curl it in. Wait.
Yeah, let me see.
Yeah.
All right, yeah.
Fine.
Well, let's say this working. Okay. What about other people? What's the reasoning the other way? Some people said E.
I had my the signs backwards in my head, so.
Oh, okay. So there's two ways we can do this, right? We can either use the way Stephen just said, which is we can curl our fingers around here, and so we know that it's making a loop that's into the page here and out of the page here, and so it's going around like this. That's one way we can do it. Another way we can do it is we can say, okay, here's my little piece of DL, and I want to know what the field is here. Well, this is my R vector, and this is my DL vector, and I know that the field is in the direction of DL cross R. So DL is this way, cross R is that way. So my thumb is pointing into the page, and that tells me, oops. So that tells me the thumb is into the page, and so this thing is got direction into the page. Right? DL cross R, and so my thumb is pointing into the page, so, like that. This one I find is easier. I think it's the one that Stephen mentioned is the easier way of doing it, and that's the one I teach first. But this way shows you how the math is actually working under the hood. This thing. So again, let's try using the Biot-Savart trick. Let's try. So which way is DL and which way is R hat on this? Current's running in this direction. So that's the first vector. That's DL, is that way, right? And then R is between the place I'm making the field and the place where I'm seeing the field. So the R vector is this vector, right? So those two in mind, which one gives you the right answer? Yeah, you guys are pointing around to it. That's the same as before. That is, so I put my fingers in this direction, cross my fingers in that direction. My thumb still points into the page. So this little bit of current is also making a field pointing into the page here. So all the little bits of current are making a field pointing into the page. right? Doesn't matter where you are along here, they're all making a field pointing into the page. So this little guy here, he's making fields pointing this way, and this guy over here is also making fields pointing this way, and similarly, they're making fields pointing out of the page on this side. So they're all contributing to making the field go into the page on this side of the thing, right? What about right above the wire? What direction is the field right above the wire? Right, it's that way, right? V cross R is to the right. No, let me see. V, yeah. DL cross R would be to the right, so it's going to be like that. And beneath the wire, it'll be like that. Okay, so that means we can take this guy and we can figure out what the total field is by adding up the contributions of all these little guys. Now, this is basically what the text has already done for you, so I'm only going to sketch it for you. I asked you to summarize this. This is briefly explain how you got this equation 28.9, what assumptions did they make, right? So a lot of people answered the second part of this question, but not the first question. I've got to say this is a great nickname. They took the BS of our line, integrated, adding the magnitudes and doing some trig, and they assumed that the wire was really long and that the point was infinite. At the wire really long to that point was infinite. The wire was straight and also carrying current. So that's what it said. It's an infinitely long wire, which is right. Portage, I'm assuming it's Portage, said something similar. They made it infinitely long, and here is the specific way in which they made it infinitely long, which is a little bit more specific, but basically the same idea. So what they did is they said, well, the field here, due to any small piece, is going to be equal to mu naught over 4 pi I dl cross r hat over r squared. And exactly how they do this is not that important, but it's worth just quickly sketching out. So if I say, let's say my point is distance x from the wire, and I'm going to look at a little current element that's, say, distance y from the midpoint. So I'll call this distance y. That means that r here is going to be root x squared plus y squared. So this is going to be, the total field is going to be the integral of all these little guys. This direction of all of this is going to be into the page. So I can just add all these up as numbers. So they're all just pointing into the page, and I know which direction that is. And so then this will just be dl over r squared. But I also have to take into account that this cross product involves a sine theta. So when I change this from this to scalar notation, I have to put the sine theta in there, where theta is going to be that angle there. But that theta I can work out because I know the opposite and I know the adjacent. So sine theta is going to be equal to x over x squared plus y squared square rooted. So if I work all this out, this is going to be mu naught over 4 pi I dl x squared plus y squared x over root x squared plus y squared. So this thing, and then here the dl I can replace by a dy, because that's how big the current is, and then I'll integrate from negative infinity to infinity, right? Now this is a complicated integral, but again, Wolfram alpha exists for a reason. And it turns out that this integral is actually quite nasty unless I make this infinities. That if I have this be less than infinity, the integral is really quite awkward, and I don't really care. So that's why we talk about a very long wire, because a very long wire gives us a simple calculation. And the answer to that calculation, which we can jump to, is mu naught I over 2 pi times 1 over x. So this is basically how far away the point is from the wire. So that actually,
is it actually 4 pi still there too?
I think this is 2 pi, but you should probably not trust me. It'll be on the correct on the equation sheet. Let's see. I can pull out the textbook. Let's see if my notes are right this time. Don't trust me. I lie to you all the time. Kirchhoff rules. Where are we? 28. And something. So a long wire. There's the current element. Aha! I was right. So in the textbook, they use R as the distance from the wire, but I'm using X as the distance from the wire. But it's the same formula. So yes, there's a factor of 2 that comes out because you're integrating over the top and the bottom. So this actually is kind of interesting because this tells you, this is kind of like what we had before when we had a long wire with charge on it. Again, we said the E field dropped off as 1 over R. It's 1 over the distance from away from the thing. And again, we're seeing the same thing here with the B field dropping away as 1 over R. And if you think about it, it kind of has to be this way because the field is only getting weaker in 2 dimensions. It's getting weaker in the 2-dimensional plane around the wire. And so it kind of has to look like this. If you have something spreading out in 3 dimensions, it'll be 1 over R squared. And it's spreading out in 2 dimensions, it's 1 over R. And it's spreading out in 1 dimension, it doesn't change. It's kind of a function of how a 3-dimensional universe works. We've reduced it down to there's only one way to get away from the wire, and so it has to drop as 1 over R. It's a kind of an interesting geometric puzzle that we don't need to worry about right now, but I'm pointing out to people who might be interested in, why the universe works the way it does. So we kind of expected something like that to happen. Okay, so we now know this is the strength of the field as we get close to a wire. So now I have an answer to this thing. If I have a current going this way and the wire is very long, or in other words, if the position I'm looking at is very close to the wire, so close that I don't have to worry about these ends that are very far away, then in that case, the strength of the field is mu naught over 2 pi times I times 1 over the distance away we are from the wire. And we know which direction it is. So in this case, I put my thumb along the right-hand direction, my fingers curl around like this. So that means the field is going into the page there, and it's coming out of the page up there. So this completes our picture of things, right? We have charges moving and feeling a force. We have charges moving and creating a field. We have a wire that's in a field of force. And we have a wire creating a field, right? So I feels B, I makes B. And this is analogous to before when we had electric fields. We have Q makes E and Q feels E, right? It feels a force. That the force here was actually very easy. That it was just F times Q. So in both cases, I've kind of got this thing. In the case of magnetic fields, currents turn out to be the easier thing to deal with than moving charges. And so we talk about the currents more frequently. Okay, so the specifics of that calculation aren't the most important thing. It's the results of the calculation that are interesting. All right, so I'm going to build up another case here. So let's start with this. Yep, correct. It's F. This is into the page, right? Never be caught by these guys. Now, so let's say I've got a field that's going into the page here. And I put another wire right here. How does that wire feel a force? All right, so everybody, let's do this together, right? The field is into the field is into the screen, right? And the current is going to the right. Am I pointing my hand in the right direction? Okay, so that's the current into the field, field. So there should be force up here, right? So this B or I cross B is this way, right? Because remember we're using L cross B is in the upward direction, so it's C. Some people are getting these backwards. Now, it's really important which one you do first and which one you do second. Remember that if you take the cross product and you invert the order of the two vectors, you'll get the wrong direction. So the order here is really important. That's why I'm always choosing the first one is like my forefinger, and then I curl my fingers in the direction of the second. People with me on this, or are people still confused by this? Okay, it's really vital that we get this one right. Okay, so let's take a slightly different one. How about this guy? Right. So current cross magnetic field gives you the force, so this guy will be pushed to the left. All right, so this is the right answer. This is the very exercise we just went through. I started off by asking, the blue creates a field. Which way is the field at this position? And the answer is the field is into the page, right? If the field is into the page right here, and then this wire is sitting in that field, it feels the field, V cross B, and so this wire is going to get pushed to the left, right? So this wire gets pushed that way because of the field this guy is making, right? Now what happens to the blue wire? What force does the blue wire feel because the green wire is nearby? And yes, I do have to use my hand for this, right? So the right answer here is B, that's right. But working this out, it's like a three-stage thing, right? I have to say, okay, here, so the green wire is on the right, do I have a green pen? So the green wire is here. It's creating a field that's pointing out of the page on this side, pointing into the page on this side. So this wire is creating a field that's pointing out of the page, and then if I put the blue wire in here, I have current crossed with B field, means that there's a force to the right. These are different colors here, right? So this guy gets pushed to the right, and this guy gets pushed to the left, right? This is what I was asking on the warm-up, right? And the problem with the answers I saw is you guys were attempting to memorize the rule for how wires attract or repel. Although that's fine, and that lets you solve this particular problem, you should be able to work it out from these first principles so you can do original problems. This is actually not a very interesting problem. It's just in and of itself, right? This isn't a situation that we see a lot of. It's just that this is a really nice way of putting together all the things we've just learned. A wire makes a field. A wire fields a field and creates a force. So it puts together both halves of the problem we've been working on so far, right? So then, of course, there's the question of what happens if two wires have currents in opposite directions. So try to work this out again using right-hand rules. Watching anybody do E&M exams is always the most hilarious thing because everybody's like doing this over their pages. It looks like everyone's practicing voodoo. I love it. Some A's and some B's. Okay, let's walk through it slowly. One of those is correct. Actually, before I move on, is there any reason why these guys are bad choices? Can you give a reason why these things wouldn't happen?
Because the current is flowing in opposite directions.
Well, we had I mean, that doesn't tell me why they couldn't both be pushed right or both be pushed left, right? Could I ever construct a case where this was true? So I'm now going back to something from the first semester. Right? Basically, the rods are pushing on each other, right? If I push on you, you have to pull on me out in the equal and opposite direction. That's Newton's third law. However, the first rod, the blue rod pushes on the green has to push on the blue in the opposite direction. Because that's because there's action current. If you didn't have that, if you had this situation, you've created a perpetual motion machine, and you could use this to go to outer space, right? All you have to do is set up two rods like this, and they'll push on each other, and they'll push on each other to the right. And so if you put them in the same machine, the machine will just start to keep accelerating to the right over all time, right? So that obviously, that's
a lot of money.
Sorry?
Probably also make a lot
of
money if you made a perpetual motion machine.
Exactly. So if this were possible, you know, we wouldn't have an energy crisis, and like this would be wonderful if it was true, but it's not true. So these guys can't be right. So we know that whatever they're doing, they have to be doing the same thing to each other. So now let's work out which one it is. So here's my blue wire. It's going to make a field. If I curl my fingers around it, it's going to make a field that points into the page to the right. So if I put my green wire in that field, the green wire feels so I have to point my fingers downwards for the direction of the current and then curl them into the page. And so I'll find that this guy has a force on him that pushes to the right. So the right wire is pushed to the right, so we know the left wire has to be pushed to the left, but let's just make sure. So here's the green wire. it's creating a field that points out of the page over here. Wait, nope, into the page. I have to do this right every time. Put your thumb along it. It means you're curling in, so the field is into the page on this side. If I put that wire in that field, then it's V cross B points to the left. So this guy will also feel a force in this direction. And so the green one's being pushed right by the blue, and the blue one's being pushed left by the green. Now, again, notice that a wire doesn't feel its own field, right? In the same way that charge doesn't feel its own field. If I put a positive charge here, it doesn't push on itself. In the same way, if I have a wire, the wire doesn't push on itself. The wire can push on other wires, but it won't push on itself. You don't feel your own field. That seems to be a general rule of how electricity and magnetic fields work. Okay, let's do a few more just to see if we can understand these ideas completely. Oh, that was pretty small. Okay, got some A's. So let's walk through the right-hand rule. So let's make sure we're right. So this is the wire. So it's pointing out of the page at us. So that means the field is going this way. So this B line is correct. That must be the B field nearby. So the B field is pointing up here. So the velocity is to the right. V cross B means that my thumb should point into the page, right? So that would give me A. What have I done wrong?
That's the force from the electron, right?
No, I'm calculating the force.
The electron has a negative charge.
That's right. I've gotten this part correct, but I didn't take into account this part. So V cross B is indeed into the page. So this direction is into the page, but I'm multiplying by a negative charge. So the electron is actually going to feel a force towards us out of the page. So you've correctly calculated this part and correctly calculated the B field, but then trip up on the last thing there. Yes, we can make this very complicated. Okay, let me give you another one. Pull this out. That's too far out. For some reason, all my D answers got not printed. I don't know why. You can imagine I've got a battery in here that's driving the current around in that loop. All right, some E's and some D's. Somebody who answered E, tell me what you were thinking.
So what I did is I did the fact that one of them is going, I did the right-hand rule for both of them, and they ended up being opposite directions. So therefore, I wasn't sure how large the current was, but they could be the same. They're in opposite directions, though, so it'd be canceling out. But then I might.
Yeah, so these have to be the same current, right? The current here and the current here has to be the same if it's a loop. Okay, somebody answered D. What were you thinking?
Oh, I was doing the other part.
Oh, I see. Someone who answered D, what were you thinking? Just jump in, don't be shy.
Well, my thinking was that there were like, because two of the arrows were pointing in one direction while one arrow was pointing in the other direction.
Oh, that's too simplistic. You have to think about what the fields being caused are. Right, so this guy is making all the fields, yeah?
So I was looking at the loop, right? And I saw that they were in opposite directions. And I assumed since they were in opposite directions, I could just not neglect it. But when I'm thinking about a net force, like, don't count it. So I looked at the top arrow and I tried to decide what the force from that would be on the loop and made that the net force.
Why not the lower one?
I don't know.
Okay. Well, your instincts are right.
Well,
yeah.
Cause it's in the same loop as the other one, and they're like, I don't know. When I looked at it, I for whatever reason assumed that they counteracted each other and not canceled out, but like.
Okay, so let's work it out. So here's our current from the big wire, and it's going to make all the fields, right? So which way is the field this guy makes down here? Is it into the page or out of the page? So right here, which direction is the field? Somebody unmute and shout it out.
Into the page.
Into the page, right? All right, so now let's take our loop. So our loop's going to be made of 4 pieces. So we'll work out what the force is on each piece. So let's say, so the top piece, that's the direction of the current. So V cross B. V cross B will be a force downward on that section of the loop. This guy's moving the opposite direction. V cross B is upwards, so it's an upward force on that section of the loop. This guy on the left, which nobody's mentioned, is down towards, and I turn my fingers in. Let me see, I can't do that on camera. So that'll be a force inwards, and this will also be a force inwards. So all parts of the wire create forces in towards the center of the wire. So now the question is which force will win? This one, or will they exactly cancel?
The down force will win
Why?
because it's closer to the wire, therefore it's feeling a stronger magnetic push.
Exactly. The field up here is stronger because it's close to the wire. This is a weaker field down here because it's further from the wire. So the force on the bottom of the loop is going to be weaker than the force on the top of the loop. So it won't balance completely, and then this loop will get pushed away from the wire. So there is a net force, and it is downwards. So if you're answering downwards, your intuition was correct, even if you couldn't enunciate it clearly. Or you can just think about it. I've got 2 wires running in opposite directions. We know that's a repel. Here's 2 wires running in the same direction. We know that's a attract. But these 2 are close, so they repel stronger, and these 2 are far, so they repel weaker.
I have a question.
Yeah.
So if in the loop the wires were going the opposite direction, would the answer be different?
So so that's a good question. Let's think about it. So I have my big wire up here running this way, and now I'll have my loop go the other way. So I'll have it run this way on the top and that way on the bottom. All right. So again, my field here is into the page. because I haven't changed the top current. I've now just reversed the loop. So now here, it's the top is V cross B. So this guy would feel a force upwards, and this guy would feel a force downwards. So this guy would be attracted to the loop. The loop would be attracted to the wire. So there, it would change. Yeah, that matters. Now, now that's my guess, but I have to. But just like you guys, I have to actually walk through that whole logic before I can say it definitively is that way, right? You should get in the practice of trying to walk through as many of these problems as you can, because practice is what makes perfect here. It's why I keep asking you variations of the same question over and over again, this is really a skill that you have to build up. And you guys are all sort of 80% of the way there to complete mastery. Some of you are at complete mastery and some of you are still making a few mistakes. But that's why I'm asking question after question. Yeah.
How would we know if there's also still arrows going downward? How would we know that it would be the net? Because we don't know the strength of any of them. How do we know that the net is still, that it's attracted?
Okay, so the force here on this wire is IL cross B, right? And the force down here is also IL cross B. So in the top example, so the length of these two pieces of wires is the same. So this part and this part are the same. And the current in this wire and this wire has to be the same because it's in the same circuit, right? And we know that the current is the same everywhere in the circuit. So the current running through here has to be the same as the current running through there, if it's all one loop of current. So those currents have to be the same. So that term has to be the same on top and bottom. The only thing that's different on the top and the bottom is the strength of the magnetic field they're sitting in. This guy on top is sitting in a strong magnetic field because he's close to him, right? Because remember, the field is equal to mu over 2 pi I over r. So this guy is a strong field, and this guy feels a weak field. So this is weak, and this is strong. So this number is a small number downwards, and this is a big vector upwards. So this guy wins.
And the large wire, that's actually, they're both heading towards each other in a sense, so they're attracting, that's why
Right, so the wire will also get attracted downwards for the same reason. And we could walk through similar logic. We could talk about what field this guy makes on the wire and what field this guy makes on the wire. And you'll find out this guy makes a stronger field on the wire, so his effect wins. So that's right, the big wire will get pulled downwards in that example, or upwards in this example, which you can know either by working out the fields and stuff again, which I'll leave to you, or you can do by understanding Newton's third law. You know, if this guy pulls on him, he has to pull on the other one, right? If one guy pulls on you, then you have to pull on him. Now, the reason we teach all that fancy Newton's law stuff, it turns out to actually, be important. So, okay, so we talked about the fields made due to little tiny bits of wire and fields made to little charges. Now I want to talk about a very useful case, which is loops of wire. We just talked about a loop of wire feeling a field. Let's talk about a loop of wire making a field. So let's say I have a loop of wire like this. I'm going to run a current through it. Let's say I'll run a current through it this way. And so you can think of it as just in some little place in here, I've got a little battery that's making this current flow, right? So I've got a little battery in here. Here's the positive side, here's the negative side. And that battery is forcing the current around in this loop, okay? Because the wire is a little bit resistive, so we'll have to have that. Or alternatively, and this is quite cool, there's a material called superconductor. Superconductor has the property that has exactly resistance equal to 0. With superconductor, you don't need that battery. What you can do is you can hook the battery up and then quickly connect, then short this out, and the current will go around in this wire infinitely. The NMR rig we have in the basement, which some of the chemists have used, the NMR rig has 0 resistance, and so in fact it works like that. The current just circles in a loop infinitely. So this guy here, so let's just talk about this little piece of the wire here. So he's going to make a magnetic field. So which way is the magnetic field he's going to make right here? In or out? You just point at your camera. Right, it's going to be in. So I curl my fingers around. And right here, it's going to be, this is in, in. And right here, it's going to be out, right? If I curl my fingers around, my fingers point out here. So right here, it's going to be, now if I move my fingers to here, again, this is going to be into the page, out of the page, into the page, out of the page, into the page, out of the page. Yeah, so check that last one, thumb to the right, fingers curl around. Yeah, it goes into the page on the bottom and out of the page on the top, right? So if I ask the question right here, what's happening? This wire is making a field that's pointing out of the page. This wire is making a field that's pointing out of the page. This wire is making a field that's pointing out of the page. This wire is making a field that's pointing out of the page. All of these bits of wire are all making a field that point out of the page. On the inside, and that's on the inside. On the outside, all the little bits of wire are making fields that point out of the page. So we can see what this is doing. Normally when I teach this in class, by the way, what I do is I get a big piece of rope and I stretch the rope around the room and I say, everybody who's standing in the room point in the direction where the magnetic field is, where you are right now. We can't do that, it's too awkward. But that would be really funny if we could put ourselves on a map. But so this is how a loop of current is going to go. Now, here's the question. What's going to be stronger, this bit or this bit? Which field is going to be stronger, at A or at B? So some people are answering B. Why is that?
I was thinking that it was just because like it would have had a stronger feel at B because it was more closer, but that was just a quick first guess. So,
well, you're right. It is close,
yeah.
But here's the second effect to think about. So let's look at this little bit of wire here, and let's just, for example, let's look at this little bit of wire here. So here's a little bit of wire on the far side, and here's a little bit of wire on the near side. Now you're right. You're close to this wire, and so this wire is making a field that's into the page. But if I look at this wire, let me see, like this, he's actually making a small field out of the page. So the field due to this wire and the field due to this wire are canceling slightly, right? He's far away, so he doesn't matter so much. So this wire is going to win. But still, they're working at counter purposes. The bits of wire on the far side, and there's a lot of wire on the far side, right, is working in a counter direction to the wire here. And so these fields cancel a little bit. But in the middle, this bit of wire and this bit of wire both are creating the field in the same direction. So here they add constructively. So what this means is that the field inside here is going to be strong and the field outside here is going to be weak. Now, we actually want to draw that. What it looks like is if here's my loop of current, so I'm drawing it sort of on its side here. What that means is I'm going to have field up here and down out here. And if I trace the whole field lines, what I'm going to look is, so for instance, if I look, so this wire is headed to the right, and if I follow this around, it's headed towards us. And if I look over here, it's headed away from us, right? So if I look, for instance, at this wire that's headed towards us, it's going to have a loop of field going around it like that. And this one's going to have a loop of field going around it like that. And I'm going to have so inside the loop, the field is going up, and outside the loop, the field is going down. Right? If I look at it in the cross section of the plane, it looks like that. The field, so looking down on it from above, the field's coming out of the loop, and on the side it's going back over. Right? And if you look at these lines are pretty far apart, and these lines in here are pretty close together. So I actually have a very strong field inside my loop, and a pretty weak field elsewhere. Again, because I'm getting cancellations from the two bits of wire. Now this is actually extremely cool, and we're going to come back to talking about this. I don't know if we're going to do it this time. We'll do it next time. We'll talk about what this means, because in fact, this pattern looks a lot like patterns we've seen before, right? This looks a lot like the patterns due to a permanent magnet, or even some patterns we've seen in electricity, which is going to be really, really important. So we're going to come back to that. I'll put a pin in that, and we'll come back to that in a minute. So one thing I can ask, for instance, So a mathematical problem I can ask is if I have a loop of current and I want to know what is the B field if I've got, say, a current running, here I'll have the current running, is that the same way as before? That's backwards as before. So let's see, so this guy, if I wrap my finger around this wire that's into the board, if I wrap my finger around this wire that's into the board, there's actually another trick you can do. That's another right-hand rule if you want to remember it, and that is if you have a loop of wire, which is a very common occurrence. If you wrap your fingers around in the direction of the loop of current, your thumb points in the direction of the field in the middle of the current. But you don't have to memorize that one. The one you have to memorize is if I put my hand around this bit of wire, my fingers are pointing into the page. If I put my hand around this bit of the wire, my fingers are still pointing into the page. So the B field here is into the page. So now the question is how strong is that B field? Well, to work that out, we know that every little bit of wire here creates a B field like that, right? So this is the Biot-Savart law. So this and here is my R vector. So DL is that way. That's a little piece of wire that's pointing to the right because the current's going to the right here. And to this guy, and then we'd have another little DL over here, and he's going that way, and he would have this R vector, right? And so we have to add up the influence of all these guys. Now we know all of them are going to create a field in the same direction. That'll be into the page right here. So what we have to do is to find the B field, we're going to have to add up all of those little bits of field. Oops, there's my piece of paper. Did I leave it in the printer? No, where did I leave it? Ah, I had a good thing for this. Where'd it go? Oh. Okay. So I'll just, right. So if I'm looking at this equation, I can rewrite this equation a little bit just to make it clearer. Right, so what I've done here is I've taken DL vector. Sorry again?
You're going back and forth between 4 pi and 2 pi.
Oh yeah, sorry, this is 4 pi. I don't know why I do that. I always want to write down 2 pi. I'm just being dumb. So this is this bit, I is I. Now here what I've done is I've taken DL vector and I've separated it out into the size of DL and the direction of DL. And so it's DL cross R hat tells me the direction, and then 1 over R squared. So here's the question. I have A, B, C, D, E. Which one of those things is constant? Or how many of those things are constant? So this isn't an ABCD question exactly. This is, so I'll ask you this. How many of these things are constant? Is 1 of these things constant, 2 of these things constant, 3, 4, or 5? You can just hold up fingers. How many of these things are constants? This guy is obviously a constant, so at least 1 is a constant in this integration. Three. Do I hear 4? I see a 4. Do I hear 5? 5. I have to have something left on the right-hand side of the integral after I'm done. So at least something has to survive, but it doesn't have to be very much. All right, so this guy is obviously constant. Is this guy constant? Yeah, this guy's constant, right? Because it's the same current no matter which section of the loop I'm looking at. The DL, that's my integrand. He's going to have to stay on the right, but he's going to be really easy to deal with. We'll get to that in a minute. How about this guy? Is this guy different? Now, this guy's a direction, right? Is this direction different if I look at different bits of the wire? Is this guy constant or is this guy not constant? Not constant. Okay. But this just tells me which way the B field points due to this bit of wire. That's what this thing is telling me. DL is the direction of the wire, and R is the direction of the arrow. But I know that this guy makes a field pointing into the page, and this guy makes a field pointing into the page. In fact, all this, what this thing evaluates to for every one is just X, just into the page. That's what this guy is for every little bit of current. This thing just means into the page. Into the page length 1 is what this thing means. So in fact, this bit is constant as well. How about the 1 over R squared? Is that constant? Yeah, because every little bit of wire is the same distance from the center of the loop. That's why we're using the loop. In R is a constant value if we go around the loop. So if we write this out again, we can write the B is equal to mu naught over 4 pi I, 1 over R squared is constant. There's the direction, which is into the page, and I guess I can call that like Z hat or something like that. And the only thing I'm left with, oops, sorry. The only thing I'm left with on the right is DL. What's this?
Oh,
What's an L? What's L in this case? As I've integrated
circumference?
the circumference, exactly, which is 2 pi R. So hey, I can work out what the strength of the field is in the middle of the coil, in the middle of the loop. The B field in the middle is going to be mu naught over 4 pi I 1 over R squared times 2 pi
Dr.
R.
Tag, next to the, you have the 1 over R squared. What's next to it?
Oh, that's a
Between
Z hat.
that and the integral.
That's Z hat. That just means into the page. Or I could call that K hat. Right, it's just the
Isn't the 4 pi supposed to be 2 pi after it's out of the integral? At least that's what happened earlier.
No, that happened. That was a result of an integration I didn't show you. I didn't actually do the integration. So in that integral, there's a factor of 2 shows up.
Okay.
Just because of the limits, because you went from negative infinity to infinity. Here, the limits are like 0 to 2 pi, and so you get a 2 pi happening here. So this 2 pi cancels with 1 of that, so I'm left with mu naught over 2 I 1 over R squared times R. That's 1 half mu naught I over R. And that's the B field in the center of a current carrying loop. Not too bad. So this actually turns out to be really useful because one of the things we can do, just to give it away, is if we want to make a strong magnetic field, what I can do is pile loops on top of each other. I can put a whole bunch of loops in the same place. In other words, I can make a coil of wire. And that coil of wire then actually, because every single loop of wire, if it all runs around in the same direction, like a spool of thread, then that means every single loop will create its own B field, and those B fields all add up in the middle. So now I have a way of creating a strong B field. Again, if we're going to talk about the NMR in the basement has got a big coil of wire that's creating a magnetic field. It's special because that big coil of wire is superconducting, and so we don't even have to use a battery. It just carries its current for forever. As long as we keep it really cold, it just keeps carrying that current forever and just holds itself and keeps a big magnetic field there. In fact, what that guy looks like is he just looks like a magnet. That's what he's actually doing there. Let's see where I want to go next. I'm going to skip that stuff. So, just to give you a teaser of what I'm going to talk about next time. I've got a single particle makes a B field. A single particle traveling in a loop is like a loop of current. A loop of current creates a B field that looks like this, which is a lot how a little magnet looks. Yeah, Yogesh? Let's go ahead and ask.
I wasn't raising my hand. Sorry, I was playing with the pen.
Oh, okay. Sorry. So this is actually going to be a clue to all of the mysteries we brought up in the first day, like what is a magnet and how does it work and why does it obey certain rules and why do the paper clips fall when you heat them up and why do different bits of metal attach to each other? All of it is contained, and why do only certain kinds of metals create magnetic fields? And this is actually the clue to it. So it turns out that what magnets really aren't little bits of metal that are with north and south on them, that magnets really are about this. And so we're going to go into explaining that next time. So that'll be what we get to when we get to there. At this point, I think we've covered enough material that you should be able to do everything in the homework. So I'm going to sort of say Monday is the nominal deadline for the homework. And so give it a try and let me know how it's going. Hit me on Slack or hit me by email if you're having problems with that. If you think that deadline's too short because of other like crap going on in your life, like let me know. You don't have to tell me what the crap is, just sort of tell me what's going on. I want to not let the deadlines ride too far because then it's going to be hard to catch up at the end, and I don't want to have a lot of work at the end of the class. That's no fun for anybody. So we'll say Monday is the nominal deadline for homework 8. I'm still working on homework 7. I think I got everyone but one, I think I've got one homework, and I've pinged her by email. I'm grading those now. I'm figuring out a way of doing this grading without having pieces of paper anymore. One thing I will say is when you're doing your homework, there's some really good scanner apps on the phone. There's something called Adobe Scan, which is free. And you can use that to take pictures. You hold your phone over it, it'll take a picture of the document and you can assemble multiple pages into a single PDF that then you can email. It's actually really, really nice. And you can even use that I'm actually thinking I might use that for my own notes. So just when I make notes, I'll take pictures of it and create PDFs on my computer. So if I lose my giant binder, I'll have it. So that's a thing you can use for submitting the next homework. I'll send out a link to all that stuff next time. Okay. Well, I believe labs are going to be due or the first part of the lab is going to be due on Friday. So if you have any questions about that, feel free to ping me. And if you have any problems or questions on the homework, feel free to ping me on this. This is going to be harder because we can't actually talk to each other.
Where do we submit the lab?
There'll be instructions in the link. So it'll be a OneDrive share folder, I believe. And that's it. So everybody have a great day. I'll see you guys on Friday.
I think my audio cut out when you were talking about the lab. What's the first part, the cutoff for that?
Oh, so the first part of the lab is due Friday at the moment.
Like what, is it the whole document?
So it's up until the electric motor. So the electric motor part won't be due. We'll do that part next week, but everything up to the electric motor we should be able to do.
Everything except the electric motor.
Everything except the electric motor. And next week we're going to add some more stuff to it. We're actually going to have fun with the electric motor because it's actually a really interesting device. So yeah, so that part up till now. But you'll have an email by the end of the day from Dr. Robertson laying this out again. So
Okay.
All right.
Is our midterm next week?
No. So I think the original schedule has a midterm next week. Is that right? I'm going to move the midterm.
April 3rd.
I'm going to move the midterm back at least a week so that we cover the same material. And just so everyone has a chance to get used to this new schedule and stuff. I want to make certain that we get at least one more homework in before we go about it. So I want to see how you guys do the next homework before we call the date on the midterm. But yeah, it's coming up, but not right away. I would kind of like to get through most of magnetism before we go to the midterm. Just so the midterm isn't too short. I'm going to figure out how to do it too. I don't know how we're doing it. I'm thinking what we'll do is I'll just send you guys the midterm and watch you on Zoom as you do the midterm. Right? A virtual classroom midterm. So it's kind of open book, right? Because I can't keep you from looking at something off camera. So it'll be something like that. Okay, have a good one.
Dr. Tag.
Yeah.
Where's the homework posted at?
It's on the webpage for the course. So I sent around a link to the new course webpage, and if you look under the homework section.
I just pulled it up and I don't see it. The last one is homework 7.
Is there not a homework 8 listed there?
No.
I was certain I had it up there. Let me double check, make certain it's showing up for me.
I see it up on the new course webpage.
Maybe you need to do a refresh?
It's under assignments and solutions, right?
Yeah.
No, I'm not getting it. Let me try to exit all the way out.
Let's see. So
Yeah, I'm only getting up to 7.
assignments and solutions. Yeah. I can see it. If I'm all right, so if I go back, so this is the new web page at github.io. That's the web page address. If you look at assignments and solutions, homework 8, that PDF is right there. So if you still can't get it, send me an email and I'll send you a copy by email.
All right.
Okay. But yeah, I don't know. It's probably you have to clear your browser, clear your cache or something. Okay. Good luck.